Hello everyone. So this is the last video for the introduction of the Green's function for the for the thermodynamic quantities. So yeah, here I'd like to show the one example of simplest example to obtain the thermodynamic potential by using Green's function. So I mean the lowest order of this series. So let me remind you about the equation for this one. So this one shows the difference between the thermodynamic potential between the interacting version and the non-interacting version. Then it can be written in terms of the thermal average of the S beta with respect to the non-interacting Hamiltonian. And then more detail, it can be written as like this. So this is some expansion of the with respect to the interaction Hamiltonian as like this. So now, as a most simplest case, I would like to show the case of the contact type interaction. So this is just most general but the simplest type of the interaction. Just so here, coupling constant is momentum independent. And now, you can see the C dagger, C dagger, CC. So some combination of the annihilation and creation operator. And now, also we are now considering as fermions. So we just consider two spin half system, 1/2 system. And now this Hamiltonian describes the interaction between the different spins. So I mean the up spin and down spin. Then, using this Hamiltonian, I like to explain how to calculate this one. But of course, this if we consider higher order correction, it becomes somehow complicated. So I like to explain the most simple case. I mean the n=1 case, lowest order case. So in this case, just we have to consider the one imaginary time integral, and now integrand is just only the v, only one interacting Hamiltonian. Then we consider this kind of the integral. Then we know the explicit form of the interacting Hamiltonian as like this. Then we can simply put them here. Then we can obtain the practical structure, actual structure of the this integrand for the imaginary time. Then also, I do not show the detail of them, but we can use Brohod-Dominicis theorem, otherwise sometimes called the Wick theorem. It depends on the final temperature of the temperature. Anyway, so we can use such kind of theorem. Then this thermal average can be decomposed to the some kind of the C dagger C or C dagger C or something. And then now we are now considering a two-component spin system, and we do not consider some spin flip in the Hamiltonians. So then just we consider the some C dagger C, but same spin here. This is up spin and this is down spin. Then so you can see this kind of the equation in the previous video. So it is actually related to the imaginary time Green's function. So I like to mention again about that as like this. So now two imaginary time Green's function can be written as like this. So C dagger, and now it has a argument of tau prime, and here is imaginary time product. Then if we want to flip this to order of this one, we consider the how to say, the case with larger tau prime compared to tau. Then this one is written as like this. So now we just put small, infinitely small delta to flip the order of these two operators. So anyway, we can rewrite such kind of interaction correction to the thermodynamic potential, and it can be written in as like using Green's function as like this. So usually such kind of correction is written in terms of Feynman diagrams. So in this simplest case, it can be written as like this. So this two loop, a solid loop shows is thermal Green's function, and this dashed line shows the interaction. So yeah. Anyway, also we can also perform the more explicit form by taking imaginary time integral or some Fourier transform to the multiple frequency. Anyway, yeah, at least we can see the clear connection between the interaction correction to the thermodynamic potential and yeah, imaginary time Green's functions in the non-interacting case. Yeah. Anyway, yeah, if we want to know the yeah, more advanced situation, you can see read some yeah, the textbook for the many-body quantum theory, quantum many-body physicist systems. Okay, yeah, that's all. Thank you very much.